In this video, we're going to have a look at the structure and properties of triglycerides and phospholipids. We're also going to have a look at the test for lipids. Let's start with a general overview of lipids. So they are large macromolecules. Just like carbohydrates, they contain carbon, hydrogen and oxygen, but they have oxygen in a lower proportion. They are insoluble in water and they are non-polar. Now, there are two main types that you need to know about. We've got triglycerides and phospholipids, and like any of the polymers we've been looking at, they are formed by condensation reactions. So triglycerides, they are made from one molecule of glycerol and 3 fatty acids. They are non-polar hydrophobic molecules, and they're formed from condensation reactions with the formation of an ester bond and loss of water. So here's kind of a general picture that you might see. So you have your glycerol molecule, you have your 3 fatty acids represented here in orange, and you have your ester bonds. So let's have a look at the individual components of your triglycerides, starting with glycerol. So glycerol, as you can see here, glycerol is an alcohol, okay? So it has 3 OH functional groups, okay, down the sides, and those are the part that form the ester bond with your fatty acids. So fatty acids have the basic structure of OH here, C, double bond to an O, and an R group. Okay, so the R group often is a long hydrocarbon chain finishing in a methyl group, and it has this carboxyl group at the end, so that formula is usually shortened to RCOOH. Now let's join them together in a condensation reaction. So here you have your glycerol molecule, and here you have that fatty acid, and if we join them together we can see that that water is lost and we have the carbon joining straight onto the oxygen. So we're just going to draw in the rest of these fatty acid chains so that we can see how that process happens. First, I'm just going to remove those hydrogens and we will bring them back later to form the water. So first up then, we're just going to add in the additional bonds here. We'll have the carbons and we have the double oxygen, and I'll draw this one below for space. And then we have that R group over here. Okay, so you can see how we can add in our fatty acid chains. Okay, so this process is called esterification, and we form 3 ester bonds and we form 3 molecules of water. So let's just summarise that esterification process. So our triglycerides are formed from condensation reactions with the formation of ester bonds and loss of water. The ester bond forms between the glycerol and the fatty acid chain, so between that hydroxyl group and the carboxylic group, and it forms this COOC bond. For each triglyceride, 3 condensation reactions happen, so 3 ester bonds are formed and 3 molecules of water are lost. This is the kind of thing they really like to add into the mark scheme, okay? So it's the 3 condensation reactions, 3 ester bonds, and 3 molecules of water are lost, okay? So your glycerol molecule, your ester bonds, your fatty acid chains. One of the main structural components of your triglycerides and your phospholipids are fatty acid chains. So let's have a look at their structure. They can be saturated, mono or polyunsaturated, cis fatty acids or trans fatty acids. So let's have a look at that in more detail. Our saturated fatty acids don't have any double bonds in their hydrocarbon chain. This means there's a complete number of hydrogen atoms around each of your carbons, okay, within your chain. So we're just going to draw that so that we can have a look, okay? So we're going to start with our carboxyl group, which is at this end, okay? And then we have our carbon chain with a methyl group at this end. So around each of these carbons, there are hydrogens, okay, with that methyl group, the CH3 at this end. Okay, so there are no double bonds anywhere in this chain, and we have a complete set of hydrogens around the outside, okay? So that is your saturated fatty acid. Now that we've looked at the structure of the saturated fatty acids, let's have a look at the structure of the unsaturated fatty acids. So these are fatty acids that have at least 1 double bond in their hydrocarbon chain. So they are missing hydrogens. So if we have a polyunsaturated, it means there are more than 1 double bond present. Whereas if it's just monounsaturated, there's just 1 double bond present in that hydrocarbon chain. So let's draw it out and see what it looks like. We'll start again with our carboxyl group at this end, and we can add in some carbons, finishing with your methyl group at this end. Now, if we are going to add in a double bond in the middle here, we can then start to add in our hydrogens, remembering that carbon has 4 bonds available. If we take this carbon, we can see that there are already 3 bonds that have been made. Same for this one, so we can only add in 1 hydrogen. Okay, so this would be monounsaturated because there's just 1 double bond in the chain. If I'd drawn in another double bond here, for example, between the 2 carbons, then it would have been polyunsaturated. Now that we've looked at the differences between your saturated and your unsaturated fatty acid chains, let's have a look at the difference between your cis and your trans fatty acids. So the unsaturated ones have at least 1 double bond in their chain, so there are some hydrogens missing, and the cis fatty acids have both of those hydrogens on the same side of the double bond. So let me show you. Here we have a fatty acid chain. Now this can extend this way and obviously at the other end as well. We have our carbon-carbon double bond in the middle here, and both of those hydrogens are on the same side of that double bond. They could be at the top or they could have been underneath, okay? But this is what we call a cis fatty acid. So they're both on the same side, either top or bottom, okay? Now this actually causes a kink in that fatty acid chain. So a cis fatty acid with both of them on the same side actually causes a kink in the chain of that fatty acid. Now this has implications for its properties. So if you've got kinked chains, they're not going to stack up nice and neatly together. Okay, so fatty acids that have a kink because they have the double bond with the hydrogens on the same side are more likely to be liquid, okay? Because they can't stack nice and neatly together, okay? They're kind of all over the place. They are more likely to be liquid. The other type of unsaturated fatty acid we can look at is the trans fatty acid. So in this instance, their hydrogen atoms are on opposite sides of the double bond. So let's have a look. Here we have our hydrocarbon chain and our hydrogens around the outside. Here we have our double bond, and you can see that the hydrogen atoms are on opposite sides of that double bond, meaning that chain is going to stay straight. These will stack up nice and neatly together, therefore at room temperature these are more likely to be solid. The other type of lipid that you need to know about are phospholipids. These differ from triglycerides because they only have 2 fatty acid chains. The other one is replaced with a phosphate group. The diagram that we usually use to represent them looks like this, with their phosphate head and their 2 fatty acid tails. Now their phosphate head is hydrophilic and the fatty acid tails are hydrophobic. This gives them certain properties that allow them to create your membranes. So if we take a look at that, due to the nature of the hydrophilic phosphate heads, so the bits on the outside, and the hydrophobic fatty acid tails in the middle, phospholipids arrange themselves into this bilayer, okay? And this is the basis of your cell surface membranes. Now we will have a video on the properties of cell surface membranes in more detail, so you can go and have a look at that. Now that we've looked at the structures of our triglycerides and our phospholipids, let's summarise with a compare and contrast table. This is a really common exam question where they ask you to compare and contrast the structures. So we'll start with our comparisons. Okay, we've got both contain ester bonds between glycerol and fatty acids. Both contain glycerol. Fatty acids on both may be saturated or unsaturated. Both are insoluble in water and both contain carbon, hydrogen and oxygen, but phospholipids also contain phosphate. Now, both is really important in all of these statements, and I've highlighted it. When you are writing your comparisons, it's key to say that both your triglycerides and phospholipids contain ester bonds between the glycerol and fatty acids, and both are insoluble in water. Let's have a look at the contrasting statements. So in our triglycerides we have 3 fatty acids, whereas phospholipids we have 2 fatty acids and a phosphate group. Our triglycerides are entirely hydrophobic, whereas our phospholipids have hydrophobic and hydrophilic regions. Therefore our triglycerides don't form micelles or bilayers in water, whereas our phospholipids do form micelles and bilayers in water. We're now going to have a look at the roles of lipids before we then compare their structure and their function. So lipids have many functions. One of their main roles is being the component of cell surface membranes that we looked at previously, and there is another video about. They have some other roles as well, and these include things like providing a source of energy. So when oxidized, lipids actually provide more energy than the same mass of carbohydrate. They also have waterproof properties, so things like insects have a waterproof exoskeleton, as well as leaves having a waxy cuticle. They are also insulating, so they can provide us with thermal insulation to keep our body temperatures the same, as well as providing electrical insulation around our nerve cells. They also provide protection, so around some of our more delicate organs there will be a layer of fat there to provide protection. Let's have a look at how structure relates to function in our triglycerides. First up, we have a high ratio of carbon to hydrogen bonds to carbon. So these are energy storing bonds, and therefore triglycerides are an excellent source of energy. They have a low mass to energy ratio. This means more energy can be stored in a small volume. They are large and non-polar, so they're insoluble in water, so when they're stored in a cell they don't affect water potential and osmosis. And finally, they have a high ratio of hydrogen to oxygen, so they release lots of water when oxidized. This provides a useful source of water, especially for animals living in dry conditions. Next up, phospholipids. So they are polar molecules. This means they can form a bilayer, and this provides a hydrophobic barrier, often between the inside and the outside of a cell. And they have a phosphate head. This allows for the formation of glycolipids within the cell surface membrane, and there are more on these in the cell membrane video. Now that we've looked at the structure of phospholipids and triglycerides, we need to go over to the lab to have a look at the test for lipids. Now that we are in the lab, let's look at the test for lipids. Today we're going to be using oil, so this is already in a liquid format, so we don't need to take our sample and crush it with water. We're going to be using ethanol today, so we need to take note of the risk. So ethanol is flammable, so we don't need this near any open flames. In order to do this test, we are going to add some of our solution or our sample to a test tube, and then we are going to add the ethanol to it. This is in order to dissolve the lipid. Okay, so we add that in there, and then we give it a really good shake so that we can dissolve that lipid in the ethanol. The next step, we are going to add equal parts water to our tube, and we are looking for a milky white emulsion forming. Okay, so positive result is that milky white emulsion that has formed. Now it's really important when you are doing the exam question that you also talk about the negative result. So if no lipid was present, then there would be no milky white emulsion formed. And that is the emulsion test. Now that we've been to the lab, let's summarise the emulsion test. Step 1, we're going to crush the sample with some ethanol. Step 2, we're going to shake that tube to dissolve the sample in the alcohol. Step 3, we're going to add equal parts water. And step 4, a white or milky emulsion will form if that lipid is present. So in this video, we have covered the structure of triglycerides and phospholipids. We've looked at how their structure relates to their function, and we've looked at the test for lipids. In the next video, we will start the structure of proteins.